In this video, we're going to take everything we've learned about series circuits and parallel circuits and use that to deal with circuits where these two things are combined. Because that's the nature of real electronics, is that we're not going to have just simple circuits all the time. We need to start to look towards a slightly more exotic, and a circuit like this one that's taken from the course notes, page 38, is such an example. We've got a resistor R1 in series with our voltage supply, and then our circuit splits into two pathways so that we have two resistors in parallel to each other. And this video and the worked example we're going to do are going to look at how we would deal with such a circuit. And as long as we remember all the rules about how things work in series and parallel and apply them methodically, we're not going to have too much of a challenge here. And the course notes it says some interesting and helpful things here. These three bullet points are worth noting. So first of all, let's consider this first one here. The voltage across R2 is the same as the voltage across R3. So what it's saying here is we have a voltage that would measure in this branch. I should really draw this as a little voltmeter. So we'd have V2 here, V3 like this, if we're measuring the voltage dropped across each one. And what we're saying here is V2 is equal to V3. So whatever the voltage is across resistor 2, the same as V3. The current through R2 added to the current through R3 is the same as the current through R1, the second. But let's see what's going on here. So what we have here, I'll change my pen color for this. We have flowing in the circuit is the circuit current. It's flowing around the circuit, and that's the same current that flows into R1. We know from Kirchhoff's first law what's going to happen is the current's going to split at a junction like this. We'll have some current going this way and some current going this way. Excuse me, I really edit that out, but we'll continue. So we're going to have our current in this point was I1, which is just the same as IC. Our current splits into I2 and I3 here. And what this is saying is that what we know from series circuits that IC is equal to I1 because I1's in series, R1's in series with the supply. But because of Kirchhoff's first law, where there's a split in the circuit, we had IC being split into I2 and I3. And we've already said that IC is equal to 1. That means we can say that I1 is equal to I2 plus I3. So that's another thing we can observe. That's our second bullet point. And the last thing we can observe is the voltage drop across R1 added to the voltage drop across R2, which is the same across R3, would be equal to the supply voltage. So let's have a think about this. And I'll erase this stuff in my diagram and write it a bit clearer. What we're saying is we've got a voltage V1 across this resistor, and V1 plus either of these voltages. So let's take V2 up here. So V1 plus V2 is equal to the total voltage. What we're saying is V1 plus V2 is equal to Vs, or we're saying V1 plus V3 is equal to Vs. It's the same because V2, as we've written around here, V2 and V3 are the same. Because what's happening here in the circuit is that voltage has been dropped across this whole section. This is V here, which is equal to V2 and V3. We could call it VP, to call it V parallel. That plus the voltage dropped across resistor 1 is equal to the supply voltage. So that's what happens. The voltage is equal across each branch of a parallel arrangement like that. But that's a lot of new stuff to take in. So we're going to do a worked example, break these things down one at a time, and then there'll be tutorial problems that we can look at as well. And once we can deal with this, we can then take anything that a question is going to throw at us because we know how to use the method correctly in order to solve a problem. So that's what the course notes are telling us about these circuits. So let's put this into practice. It gives us quite a decent worked example on page 39 of the course notes that we'll work through just now. So this is a worked example, and it's actually just like the circuit we've got here, but with some numbers in it. So let's have a look. So first of all, we're going to be asked to find the total resistance in the circuit. Well, we don't quite know how to do this, so we need to take a think about it first of all. So the first thing to observe is that we can work out the total resistance of this part of the circuit here. Where it splits, if we can work out, because we know when we've got two resistors in parallel, we can work out what their total resistance is. So what we're going to do is, rather than calling it RT, because it's not the total resistance circuit, we're going to call this RP, representing the parallel bit of the circuit. It's found in the same way. If we find a total resistance in parallel, we're going to have, well, in this case, let's keep our resistors consistent. If we look back here, our resistor numbers are going to be 1, 2, and 3. We're going to have R2 times R3, that's the two that are in parallel, over R2 plus R3. So the total parallel resistance is going to be given by 48 times 10 divided by 48 plus 10. So this is our standard formula for finding two resistors in parallel's total resistance. We have 480 divided by 58. And that's equal to a bit less than 10, but I think we need something more specific than that. Is equal to 8. I'll keep it to 3 decimal places. 8.276. We're now 8.276 ohms. We can round that up in a little bit. So that's our parallel resistance. And so now we can treat this thing, that bit in the blue circle, as if that's in series with the resistor 1. We can just add, because the total resistance across this section is now part of the circuit. So our total resistance for the circuit is going to be R1 plus the total resistance of the two parallel branches. It's going to be equal to 24 plus 8.276. I think we can see I have rounded to a few too many decimal places. I'll round up to one more, and that's going to add up to 32.276. And I'll go with what the course note says and call it 32.28 ohms. So that's how we find the total resistance in a circuit like this. We work out what the resistance of the parallel branches are, and then we add it to any resistors which are in series, in which case there's one resistor here, so we just add that R1 on to RP for the parallel branch, and that's part A of this question. Now we can look at the circuit current. Now this is exactly what we've done previously. When we know the total resistance and we know the voltage supply, the circuit current is found by our voltage supply divided by our total resistance. In this case, it's going to be 12 divided by 32.28, and that's equal to 0.37 amps. So this is just applying Ohm's law, as we've done in many other questions in both series and parallel circuits. We're now asked, I'll rub this blue circle out just now because it's getting in the way of some of my questions, but we're now asked to find the voltage drop across resistor 1. Well, resistor 1 is in series, so it's something that we know the current in already. In resistor 1, the current is the circuit current. So we have this 0.37 amp current, and the resistance of resistor 1 is 24 ohms. So we have all the information we need to apply Ohm's law to find it. V1 is equal to IC times R1. 0.37 times 24 gives us our voltage across resistor 1. I should make that look a little bit more like a 24 there. And the answer we get is 8.88 volts. Now, we're then asked to find the current through resistor 2. Now, let's have a think about how we're going to get this. What we know about resistor 2 currently is the resistance of it. And I can just see now, and I'll make a wee quick correction here, that the course notes have chosen to label our resistors the other way around. They made this one 3 and this one 2. So resistor 2 is the bottom. It doesn't actually make a difference to this, because even though I'll just fix it up here, because we can do this either way around. So I've done it as R3 times R2. The order doesn't matter for that, so that's absolutely fine. That stays the same. So it's a bottom resistor working out in part D. So we want to find the current through resistor 2. Now for resistor 2, what do we know? Well, we know its resistance is 10 ohms. But we don't know the voltage, and we don't, and the current is what we want to find. But we can find the voltage, because what we know here is the voltage across both resistors 2 and 3 is going to be the supply voltage minus what we have taken away by resistor 1. So what we're going to have here is we're going to have a voltage 1 across here, and we're going to have a voltage across the parallel section as well. So we call that a VP, and that's going to be the voltage through each of those two branches. Take that away, so now to make it a bit hard to read. So our total, if we go back to this, our voltage supply is equal to the voltage dropped across resistor 1 plus the voltage dropped across the parallel section. So we've got a voltage supply of 12, the voltage across resistor 1 is 8.88. So the voltage across the parallel section will be 12 minus 8.88, and that, of course, is 3.12 volts. And that means we've got 3.12 volts running through resistor 2 and through resistor 3. So we have our voltage now across resistor 2, which is 3.12 volts. And of course, with the voltage and the resistance, we now have enough information here in order to work out the current running through resistor 2, which is going to be given by I2 is equal to V2 divided by R2, which is 3.12 divided by 10, giving us 0.312 amps as the current in resistor 2. So, apologies, I confused that slightly in there by swapping my resistor numbers around, but hopefully you can follow through and see how we've done all of this. The key to the final part was knowing that in our circuit, the voltage is going to be divided up between what we have in resistor 1 and that parallel section of circuit. And once we know what's across the parallel section, we know that the voltage in each branch, so through resistor 2 and through resistor 3, will be the same. And we can use that with the value of the resistor to find the current in either resistor. And we're asked for it in resistor 2 here, so that's what we have found out. So that concludes the worked example. We can move on now to the exercises on page 42. There's 3 questions here looking at these types of problems. So I'd encourage you to go and look at that just now, and you'll see in particular question 1 in that page is very similar to this tutorial problem. So this worked example. So this should hopefully help with the tutorial exercises.